like crystals. They've treated me well. They're fascinating things. But they're physical objects that are limited. Okay, choose whatever analogy you want. Okay? From marriage to glasses. Whatever you want. Okay. We're trying to work around it. And the way to work around it these days is to go digital. Okay? What I want to use is something called a spatial light modulator here. This is a little screen. You can view it basically, there are two versions of it. A million little mirrors. So if I take a mirror that's pixelated and I move it back a little, I don't absorb the light in me, but I change the path length. Right? Changing the optical path changes the phase. I can now make whatever phase pattern I want. And I can do this these days at about 10 kilohertz, if you pay enough money. The other alternative is to take your laptop screen, right, which has a bunch of pixels in it, all sorts of megapixels, liquid crystal. You shine your light on it, there's some pattern here, and when the light reflects off, it acquires that pattern. I've spatially modulated my light. Too clever with their names. But it lets you do all sorts of wonderful things. Right? For example, I can take the statistics of the light coming out of the projector and change the statistics. I can go from Gaussian to Lambertian if I want to do astrophysics. I can do edge kind of modulation if I want. I can locally change the statistics through coherence engineering, or really any form of designer illumination I want. And what I want to do here is I want to measure my object and change the illumination as a function of my object. So I make it mathematical. Right? That can be pretty much whatever I want. I can move my mirror in response to the intensity a little bit or a lot with any functional form. And now I'm not relying on physical charges or response of a crystal. I'm relying on a computer-generated motion of a MEMS device. So that doesn't depend on intensity. And I can make it depend on intensity. And I can do it quickly with whatever form I want. So here's an example. The experiments are relatively simple. I have some object, I take an image of it, I make a phase modulation on my modulator proportional to that object. So there's my nonlinearity, and take another measurement. So if I have something that's basically a phase object, you see the edges show up because they're edges here. And I diffract, I defocus, I get some fringes. And if I reproject that onto here, I get twice the fringes. And I basically propagate it twice as long. And that's controllable. More fringes means more information. So I should get a better result. Which I do. So the green part's the nonlinearity. You can see it go twice as deep right here. I get the same type of behavior, a resonance condition, because it is a nonlinear problem. Without the crystal now, it's electro-optic. And I can do this for coherent or incoherent light. It's just a mirror. It doesn't care what type of light is going on. So depending on the coherence and the spatial features of my object, I can basically get 2 to 3 times as good a metric as the linear case. Contrast signal to noise resolution. You win not only individually, but in combination. Things that cannot happen in linear systems. The trade-offs no longer apply. And now you're off to the races. Okay? This is actually a very general principle. Nothing I've said applies specifically to light. Any wave will have this as long as there's a nonlinear response. So if I want light, and I want to do things like microscopy or tomography, I want 3D information, isn't it nice, instead of having uniform illumination, I can design that illumination based on whatever I want. And one argument would be, the best possible illumination I get depends on the shape of my object. I've tuned it from the beginning and maxed everything so that I can win as many counts as possible. And one thing I'm particularly excited about is applying this to ultrasound. Because ultrasound has been kind of an orphan child now for a couple of decades. If you're a sharp kid going into biomed, you're probably going to be attracted by sexy, shiny things. And I don't blame you. CAT scans, MRI, PET scans, right? All the expensive stuff with high resolution and so forth. So it turns out there's several generations of ultrasound that have been basically skipped from a scientific sense. Technology's advanced, just like it has in optics, and we can apply these techniques to ultrasound. And it's very easy to make a nonlinear acoustic response. So one real promising case, for example, is batteries. Right? You can see here, even a 1D case, this is just transmission and reflection. It turns out, as you charge and discharge, right, you're changing the density of the battery. You change the sound speed. You shoot it with sound, I can now look inside and get the charge distribution. I can see the fading cycles in lithium. I can actually probably pick up phase transitions on when they go critical. And if you recall, the Dreamliner Boeing 777 was grounded because their lithium batteries kept blowing up. It's a critical phase transition inside that's really hard to determine. And precursors aren't there, but you can pick up on it. In tissue, highly nonlinear. You don't have to do very much at all to make a tissue nonlinear. Not at all. Okay? And now I have this method of comparing linear and nonlinear and gleaning out differences and so forth. Right? And tuning for edges and looking for different features and things like this. Sometimes you need a technician. Eventually you're going to start automating this and making feedback loops. Okay. And if it works for any wave, okay, let's make it work for a quantum wave. Okay? The best you can do. As I said in the beginning, nonlinear crystals start quantum optics. You go the other way with a high energy photon splitting up into two low energy photons, conserving energy and momentum. And historically, quantum optics has basically been done in one experimental way. You take these two photons and you take a point detector, okay, a photodiode that is very sensitive. Sensitive enough, obviously, to pick up on one photon. And since they're born at the same time, at the same place, you want to measure these guys at the same time. You want to do a coincidence measurement to make sure that you're measuring two photons that really were born together, really were contained. And typically, you deal with two polarizations. Okay, just like spin up and spin down for electrons, horizontal and vertical polarization, you don't know which is which. There's your 0 and 1, there's your quantum bit, there's your quantum information. Almost no imaging is done like this. Because if you want to image with point detectors, you'll have to take them and sample every point in space. Then move over and look at the correlation, horizontal and vertical. Okay? That is a lot of measurements. Very tedious, very time consuming. Okay? So much so it's past the threshold of most grad students. Okay? Nobody does it. Fast forward a little bit with technology. Megapixel camera, 1 million point detectors. Okay? I can't photon count. They're not good enough yet. But what I can do is I can lower the temperature and make them sensitive to low photon number. And now I just take a picture and watch what happens with all of these spatial modes that make up the image. So instead of two polarizations here, horizontal and vertical, and those are the ones that are ambiguous, right? I don't know which is which. The photon, when it flies off, spreads out, and there are 1,000 modes horizontally and 1,000 modes vertically. I have 1 million spatial modes, and the photon could be in any one of them. That is a much bigger dimensionality for entanglement, for correlation. It's a different kind of problem. And one of the very first experiments on imaging that was done was this Brita experiment, where they took two photons that flew off at different angles and put an absorption mask here. So you take some pictures, it's pi. And then the bottom photon just goes free through the slide. And the idea here is that there's noise in this measurement. There are fluctuations. And because the two are highly correlated, right, quantum entangled, fluctuations in the top match the fluctuations in the bottom. They're related. So if I measure these guys and subtract, I remove the background fluctuations, I get better noise properties. My signal-to-noise ratio is much better than classical imaging. The price I pay is that I've separated these two out, and I absorb the photons. It's also a highly artificial problem, because if I want better signal-to-noise, I'll just turn up my laser power and get better signal and overwhelm my noise. So nearly all quantum imaging problems are concocted to reduce the background rather than raise the signal. You also basically leverage one photon instead of both. I'm going to do things in a slightly different way. I'm going to take a phase mask so there's no intensity absorption. I want all the photons that enter my object to actually make it through to my camera. And I'm not going to split them up, one going this way and one going this way. I'm not going to sample over here and measure over here. Okay? I'm going to put them both together so they double up the properties. They go in step. And here I want to take a step back and remind you of what's kind of unique about quantum phase. So on the right here, we have Heisenberg, position and momentum uncertainty, as we all know about. But we often forget that this relation, or these relations here, have nothing at all to do with quantum mechanics. They're wave dynamical effects. In fact, I can factor out the h bar and cleverly have that drop out of the system. And that's because points obviously tell you where things are localized, and an ideal wave is infinitely extended. Those two ideas are incompatible with each other. They're dual spaces. In fact, the only way we can make a compromise between them is to take a wave packet. Some localized wave, like a Gaussian here, that minimizes this uncertainty. Okay, this is just a Fourier relation telling you that they're dual spaces. Position and derivative. Okay. Where things become truly quantum is when you start talking about discretizing and the number of particles or the energy. Okay. Once you start talking about a photon in this International Year of Light, okay, a photon is quantum. And one way to easily see this is you take your energy, and it's made up of a certain number of photons here, and at a given frequency, the pump laser is a given frequency that generates my daughter waves. I get a different kind of uncertainty relation, number and phase. And that's truly the quantum optics expression. Even though here you can see there's no h bar. That's that number. And this shows up in some really fascinating ways. So let's suppose I take a kind of the simplest experiment I can do. I have a pump wave here. I generate these two daughter photons, and they're entangled. Born at the same time in the same place, I take two mirrors, and I bounce them back and try and interfere them. Right? If they're really correlated, right? If there's, in fact, as coherent as possible with each other, I should get interference. The only real question is, what's my interference? Right? Is it normal one photon period, lambda? Is it lambda over 2, where I get higher resolution because these accumulate faster? That's the theory. The theory is if I have n entangled photons, I should have lambda over n resolution. And it turns out when you do the experiment to interfere them, you don't see any interference at all in the intensity. And this is the laser, the pump laser. You do see interference. And it's a really bizarre effect. And the reason being is this quantum uncertainty. If I know that there are two photons around, then my phase is completely indeterminate. The uncertainty is basically infinite. And if I don't know my phase, I can't get interference. Destructive or distractive interference. If I take a coincidence measurement, though, measure these 2 points and look at their correlation, I do get interference fringes. And in fact, I get twice the frequency, the lambda over 2. This is a higher order of coherence. This is what led Glauber to the idea that you have to take correlation measurements, 2-point, 4-point, and so forth, that won him the Nobel Prize for quantum. There are differences between intensity and correlations, which is true classically as well. Classical statistical physics gives you this. The second consequence is what troubled Einstein. What you do, you take a look at these two photons that fly off, you measure the position of one and the direction of the other, the momentum. But because these guys are correlated, as soon as I know one of them's flying off in this direction, I know that the other has to be flying off in the opposite direction. Like so. Which means I know the position because I've measured it, and the momentum because I've inferred it much better than Heisenberg would suggest. Okay, this is the original EPR paradox. So if you have this kind of phase uncertainty because you have two photons, and you have this phase trouble because of EPR, right? do you really want to go out of your way to do phase imaging with quantum light? And especially if you're an academic, the answer for sure is yes. And then eventually, right, this will come into practice. Sony, for example, has patented a photon counting camera. So it's coming online. And we want to take pictures of it here so that we can actually see what we're doing in the extended spatial lines. So this is what an experiment looks like. I don't actually see a picture very well because my intensity is so low. My photon count's really low. I get random bright spots as my pixels light up. Okay? And I can't count these guys. I have to keep the shutter open for, I don't know, maybe 50 milliseconds or something like this, and just let all of this accumulate. But I can certainly take a beam, this is just a Gaussian beam, although you can't tell, image, and then I put a lens and I do a Fourier transform. So there's my position, there's my momentum. And in order to actually see something reasonable, I have to take a whole bunch of these frames and watch my signal build up. And then all of a sudden, I do get a Gaussian beam. This vertical stripe is readout noise. It's an artifact of camera. And the fun part about Gaussians, of course, is that the width of them is their uncertainty. So I just measure this and I can say, there's my spread in x, my spread in position. I look at my Fourier lens, there's my spread in momentum. And I multiply them together, delta x times delta k, and I get an answer that is far lower than Heisenberg would suggest. So it's true, quantum mechanics is non-local. That's the whole point of the experiment, and Bell's inequality and so forth, right? So arguably, the last few decades of quantum research has been more and more decimal places on how well you violate Bell's inequalities and so forth. This is a measure of how my beam is entangled. And the solution to the paradox is it's not fair to apply Heisenberg's idea of a one wave packet limit to a composite particle here that's got one piece and another piece. I can't just apply Heisenberg to half the problem and then plane my beam then. But now what I want to do is I want to take my quantum light and image a phase object. And yes, the phase is indeterminate for each of the photons, but they go through a phase mask, and each one acquires a certain thickness of optical path, a certain phase difference. And it's that phase difference I want to pick up on. And I'll do that by defocusing and watching what happens as the phase turns into intensity. So I can measure my camera. So here I have an S, it's in focus. So all that's a flat phase, I get some edge effects. There's my pump beam. Watch what happens when it defocuses, not very much. But the biphoton that comes out, the photon pair, defocuses quite a bit more. Okay? It's accumulating phase faster. And it could accumulate phase faster because it's a longer wave, so it has stronger wave effects. Or it could be accumulating it because it's a photon pair that's doubling up on its efforts. So I can take a reference beam at basically the same wavelength and watch what happens, and I don't diffract very much at all. There's something about the pair that lets me accumulate phase faster. And if I then do my phase retrieval to say what that is, and look at the noise, what I wind up with is that I get a much flatter phase reconstruction in the quantum case. And if I look at that a little better, this is the root mean squared noise. I basically get a factor of 2 better in my noise properties, signal to noise, than I do in the classical case. This is the best result to date. In almost every experiment so far, you take your photon pair and you separate them out. So you sample here and you measure here, and you don't get the full effect of the quantum nature of it. You get basically a square root of 2 improvement. For us, we take them in line, we double up, and you get nearly a factor of 2, which is what Seth Lloyd predicted for quantum illumination. If you have n photons, you get this factor of n, not square roots or other powers flying about. So the next step is to try and entangle more of these guys to get higher and higher effects. Okay. Now, we get better noise properties, but the question is why? There's something about it. Let's see if we can narrow it down. And this is where I'll end up. It turns out that your correlation properties of your beam change when you propagate. And this is true classically too. If I have some statistics, right, rays going off in all directions, and I let them go, that statistics can change. It can evolve. It can also evolve in the quantum case. Entanglement itself can propagate. So I can not only defocus on my detection end to see phase into intensity, I can defocus or separate out my mask from my source here and control the degree of entanglement based on where they're generated. I'll do a simple measurement with the Gaussian beam. As I start moving my detector away, you can see my correlations go down and down. And eventually they basically get to 0. One way of looking at this, they're born at the same time in the same place here, so if I know one photon's here, the other one's right on top of it. They're perfectly correlated in space. But as they start flying off from each other, if I measure one over here at x, this guy's at minus x. They're anti-correlated. So if I go from positive to negative, there's a 0 somewhere in the middle. And I can operate experimentally at that 0. So I can take a look at my phase image, okay, what I get in my camera, with spatial entanglement and without spatial entanglement, and see if there's a difference. Separate this and separate that. And if I look at my camera, just at the intensity, this is what I see. It looks exactly the same, which is all right. I'm not going to panic, because I know that if I do things like interference measurements with 2 photons, I don't expect to see things. The phase is kind of funny that way. It's higher order correlations. I have to somehow look at kind of a pair correlation, even though I don't have any coincidence measurements. 0 spatial entanglement, and that's an artifact. And the width of that gives me the degree of spatial entanglement. Now, because of momentum conservation, the angle at which these photons fly out, the width of this guy, I can control by changing the angle of my crystal. So what I'm going to do is I'm going to change that angle ever so slightly so that instead of being right on top of each other, their average separation distance is nearest neighbor pixels in my camera. So here's my measurement. I get a cluster of spots. If I see 2 pixels right next to each other light up, the odds are good that it's a pair of photons that are doing it, rather than 2 individual photons that happen to be next to each other. I cannot do this problem in general. I can't say, this cluster of 3 by 3 pixels is because 9 photons are entangled. But for a pair of nearest neighbors, I can be reasonably confident. And I can subtract out all my single dots from all my pairs of dots, then look at the image I get. And in one case where there's no spatial entanglement to my source, I don't see anything. When there is spatial entanglement, my image pops right out. I need spatial entanglement. I need both pairs here operating in concert in order to convert this deterministic phase change into intensity. And if I collect more data, I get better and better pictures. Basically just background noise versus something that's very clear. And it leads you to some really fun interpretations. Okay? Because if I need both of them there, this is quantum interference. This is their correlation, their coherence. So I can take basically my experience with classical interference and translate that into quantum waves. Just like all Feynman disciples do. You take your wave and you square it, you get interference. So in one case, for example, I might have a photon flying through my system that doesn't really get a phase change. It's just background. Another part gets deflected a little bit with my signal. That looks just like a hologram. Right? A self-referenced hologram. But it's a quantum beat. Or if you want, they're flying off this little angle as nearest neighbor pixels, so they sample different points of my phase object. Different phases gives me, right, an interference pattern. This is differential interference contrast in microscopy. Typically, you need polarizations to make sure they only interfere when you want them to. Here, they interfere because it's a quantum event. And that's where I'll stop. That because of this beauty part of the nonlinearity, okay, it's not just one photon at a time doing its business. You have many photons there that are interacting and being correlated. That's an extra physical effect which you can engineer, provided you understand it. You understand the physical entropy of what's going on, you translate that to informational entropy on a system level. You do something here that you know, and you translate it here to an object you don't know, and get better results. And because it's not linear, and it's not classical, right, you get better results than you get classically without the trade-offs that you suffer from ordinarily. And then eventually, because of technology, what we have now is not point detectors and TD's experiments. It now looks like any other imaging experiment that you do at the expense of a higher priced camera. Right? And a slightly fancier source. But the source is easy. And we have these spatial light modulators to control the waveform, which we can then base on our object and make it mathematically nonlinear. So we can have whatever light intensity we want, whatever mathematical form we want, as long as we choose our metric to say, what is it you want to optimize on? Which makes the field wide open. Thank you.
Very nice talk. Okay, questions? Chris?
Kind of going back right to the start, really. You mentioned that you use a video crystal, I think, to effectively scatter in high space frequency photons back into the system after.
For that one, it's going to be an SPN crystal, so it's like lithium niobate.
Okay, cool. The question is, I mean, does that really count as a nonlinear? Because I could just put a known pseudo-random faceplate at that point, and I effectively do the same thing. I scatter photons that would be going that way back into the matter.
That's correct.
What's the kind of fundamental benefit of doing the nonlinear case over the kind of redirection case?
It's intensity dependent. Is the only added benefit of nonlinearity. So you get two effects from that. From a pseudo-random pattern, it's a fixed pattern that you put in. If it's intensity dependent, whatever the object looks like, it creates that pattern, that index change. So the pattern you make is a function of your object, which means all the features there are automatically matched. So it's not randomly going off and so forth. The pattern itself reinforces the image you get after, which is helpful. And if you're doing something like phase, you get this added kick because there's an intensity contribution that gives you that resonance. So you have a stopping point, it's non-monotonic. You know when the optimum is and so forth. So it's really that phase match, it's the object dependence that helps you win. But other than that, you're right. There are many ways of getting better resolution or better field view.
Question?
So in that last part, you're looking at, you have a camera and you have these pixels that are lighting up. And you look at coincidence measurements between two neighboring pixels, let's say, because you slightly diffracted it so that it comes off a little at a different angle, if I'm understanding that correctly.
Yes.
So then, just out of curiosity, so then you look at the temporal correlation between those two pixels, and you say like when they're coincident, when I see two photons simultaneously, that's coming from a single. I guess I'm a little confused because how do you have that temporal? I mean, the temporal resolution is going to be your camera speed, right?
Well, since we've become fast friends here, I cheat. I can't tell at all about temporal response. Okay, so here we go. Right, this shutter's open a long time.
Yeah.
Right, so I get 100,000 photons or something like this. I don't have any time information at all about that. I'm just making an assumption that if they're nearest neighbors, then the odds are good. It's because the pair is there, rather than something random. And there will be some error there. I have not yet characterized how bad that error is. I don't know. But I do know I get a very reasonable result from it.
A little earlier than this, you talked about the improvement in your signal's noise, and it sounds like you're basically beating the shot noise limit for photon counting by using a nonlinearity. Is that just because you either get 0 photons or 2 photons?